Dr. Wade, so good to meet you.
Good to see you.
Absolutely. Gonna show me some good stuff?
I am. We're about ready to go back to the lab here, show you our pellet lab. I got some glasses here. We got to be safe.
Thank you very much. Thank you very much.
Make our way.
So we're here at Oak Ridge National Labs, where scientific research is searching to answer some of the greatest questions in the world. And specifically, we're here talking about energy. How has Oak Ridge National Laboratory transformed our understanding of research and the future around energy?
We're looking at future ways of doing energy. We're doing battery research. We're doing biofuel research. We have a whole division devoted to how do we do nuclear energy better. But my division is fusion energy, and that's where we're trying to take this power of the sun and the stars and bring them here to Earth to make an inexhaustible source of electricity for the future.
So let's just begin from basics. What is fusion?
Fusion is a nuclear process in which two atoms, small atoms, come together and they make a larger atom. When you do that, you release a lot of energy. Per gram of fuel, you release 1,000,000 times as much as you do when you're burning a piece of wood. And so you have a source of energy that's enormous. And this is how the stars, the sun, all of those were formed through this nuclear fusion process. We're just trying to capture that here on Earth and make electricity out of it.
Let's unpack that. I mean, why is it so hard to develop that so we can use it for everyday applications?
This process only occurs when you get the atoms to a very, very high temperature, like the sun. And so we have to recreate that environment here on Earth. We can't just put it in a vessel and say heat it up with a microwave. We have to actually create plasma. A plasma is where you just take a gas and you heat it up really high temperatures. And what happens is the electrons pull off from the atom. And so you get this gas of ions and electrons. And this gas of ions and electrons have this interesting property that they follow magnetic field lines. So if we create a magnetic bottle, we can confine those ions and electrons. As we heat them up to very high temperatures, they stay inside the vessel, and we can just heat them up until fusion occurs.
So we can actually heat up these ions and electrons in a plasma so hot that they might get to the temperatures of the sun, but as long as we wrap it around with a magnetic field, we can contain that energy so it's not harmful to us?
That is absolutely right. That temperature is really hot because we have to get there to do fusion.
So we're here in the pellet injection lab. What do you specifically do in this lab space right now?
So one thing we're trying to learn how to do is how to sustain a very long pulse fusion. Like the sun burns forever. We have to do something like that in the lab for a very long time. And what's really important about that is how well we can fuel it, how we can get the wood into the fire to keep it going forever. So we have this very hot plasma. We got to get fuel inside that. How do you do that? I mean, everything will just melt as it gets closer. So what we do in this lab is we've developed technology where we can take hydrogen and freeze it to very, very cold temperatures. So almost the coldest temperature you can get to on Earth.
Okay.
And we then accelerate that pellet into this plasma, and it will, because it's so cold, it will take some time for it to disintegrate, and it can fuel the plasma. In this chamber here, we form the pellet. Looks sort of like this. A gas pressure tube behind it pushes the pellet, accelerates it up to 300 meters per second into that chamber.
Can you show me?
Yeah, I can show you. In this video is the pellet coming out of a tube. And in this case, we've intentionally broken up the pellet before it gets to the end of the tube. And what you're seeing in this video is those high-speed fragments coming out and entering into the plasma.
So what happens after those high-speed fragments enter the plasma?
So in this particular case, we're using this to rapidly fuel the plasma. We're trying to keep it from causing damage to the vessel. We're injecting the pellet and we're cooling it off really quickly, and that will just cool the plasma off, and then it won't hit the walls and melt them.
Can you talk a little bit about ITER?
Yeah, so ITER is this large international collaboration. This is a collaboration amongst most of the major countries of the world. They are building it in France, but the U.S. Oak Ridge National Lab is the lead lab in the United States for in-kind contribution. Its goal is to produce 500 megawatts of energy for 400 seconds. And so you would think about that, that might not seem like a lot, but the 400 seconds is enough to make sure all the subsystems have gotten to a steady state and they can operate reliably for very long pulse. And 500 megawatts is getting very close to what you need to actually turn that power source into a power plant. A typical nuclear power plant is like a gigawatt, so 1,000 megawatts. 1,000 megawatt facility supports a city running full blast, right? I have every house electrified, every business electrified. And so ITER would be capable, ITER class, a little bit bigger, would be able to do that. What's interesting about that, though, is that in creating that 1 gigawatt of power, you only need 3 little liter bottles of fuel. Whereas for a coal plant, you need 80 railloads of coal every day to do the same thing. And so in fusion, you would do that with 3 liter bottles each day. The problem with carbon is it's producing a lot of waste at the same time, whereas fusion, you're burning all of that fuel up and you have very minimal waste.
Best guess, when do we think we'll have fusion technology available?
Technically, there's no reason we can't be ready in 15 years. If there is an enormous influx of investment and new people into the area, we could do this in 10 years. I think the future of fusion is extremely bright. The beauty of fusion is that there are no greenhouse gases, has very limited long-term waste disposal that you have to deal with. It has a fuel that by conservative means is available for the whole world for 15,000 years. If you go to more extreme means, for millions of years. And so it could be that inexhaustible energy source for mankind for the future.
Such a pleasure to chat with you.
Awesome. Thank you.